In this paper, we designed a haptic feedback method for a virtual button based on a real physical button. A physical button provides haptic feedback throughout its full travel range. After a finger touches the button, then the finger pushes it until the actuation point. At some point, it suddenly collapses and it generates a vigorous haptic feeling. After this, it reaches its full travel range and the movement is blocked. However, most virtual buttons on the mobile devices provide haptic feedback only at the touch and release moment of the finger movement. We think that this is clear on oversimplification of the haptic feedback of a real button. We want to design more realistic virtual buttons by providing a haptic feedback before and after the point of collapse. This is a force displacement graph that represents the force feedback characteristic of a typical physical button. We divided this graph into three sections: a slope, jump, and a bottom out. At the slope, a button is smoothly flashing down, and the displacement is proportional to the finger pulse. Jump is a sudden displacement change at the point of collapse. After another slope section, this button reaches its maximal travel. It is called bottom out. To replicate this button movement on the mobile device, we implemented a mobile phone mockup with a force sensor and tactile actuator. From now, we will explain feedback signals generated at each section of the force graph. For the slope section, we adopt the idea of haptic grain model. Conceptually, it is scratching bumpy surface when it moves. As force applies, it scratches the grain which is evenly distributed. When you scratch a grain, a tactile actuator generates a brief grain signal. For the jump section, it produces a burst of vigorous signal. It will provide a strong and distinctive vibrotactile feedback. When it reaches its maximal treble, it generates bottom-out signal. This signal has been designed to provide a sudden stop sensation. To evaluate the effectiveness of our system, we designed the 6 different virtual buttons based on the real physical buttons. As evaluation, we conducted 2 experiments. From the AVX pairwise discrimination test, the answer rate was 94.1, even in a noisy environment. Also, participants could associate 4 virtual buttons with their physical counterpart, with a correct answer rate of 79.2%. Thank you for watching.